Every day, this highway handles tens of thousands of vehicles, carrying thousands of tons in constant traffic load. Normally, repairing the road surface would mean shutting it down completely for months. But in Switzerland, engineers came up with a different solution: a mobile construction bridge system, precisely engineered to support real traffic loads while the entire road underneath is removed and rebuilt. So how did they make that possible? Let's find out. The ASTRA Bridge is a mobile construction bridge designed by Swiss engineers specifically for highway maintenance. While road work is carried out underneath, traffic can continue to flow over the bridge on 2 lanes at speeds of up to 60 km/h. This allows construction to take place during the day without closing lanes or diverting traffic. The most important feature of the bridge is that it is mounted on wheels and can be moved. It can be transported and installed by truck, making it easy to relocate between different construction sites. Another key advantage is its extremely fast installation. The bridge can be assembled and ready for use overnight, minimizing traffic disruption. The bridge is fully designed by engineers using specialized CAD/CAM software, where every steel girder, load-bearing rib, and connection point is modeled with millimeter-level precision. Before a single weld is made in the workshop, the entire structure is already calculated for load capacity, deflection, torsional behavior. The main frame of the bridge is fabricated from high-strength steel plates, formed into large modular sections inside the factory. Components weighing tens of tons are positioned using specialized lifting equipment, then joined together by highly skilled welders who complete thousands of meters of continuous welds under tightly controlled conditions. Each joint is not only visually inspected, but also tested using non-destructive methods such as ultrasonic or dye-penetrant inspection to detect microscopic defects hidden inside the metal. Before being transported to the construction site, the bridge undergoes a critical outdoor testing phase. In the test yard, the entire structure is activated and moved across a concrete surface, closely replicating real working conditions. Engineers monitor stability, steering behavior, and the response of the frame and wheel assemblies under simulated loads. Only after passing all these tests is the mobile bridge approved for transport and installation, ready to operate in real traffic conditions without interrupting the flow of vehicles above. The completed ASTRA Bridge has a total length of 256 meters, including a 100-meter elevated section designed to allow construction work directly underneath. The structure provides a clearance height of 3.1 meters and an underbridge width of 5.1 meters, giving construction vehicles ample space to operate, while traffic above continues to flow normally without road closures. Before installation, the entire assembly process was carefully simulated to avoid any errors. Traffic on the motorway was reduced to a single lane and guided through the emergency shoulder. The entire bridge system was delivered to the site in 47 heavy-haul transport trips, each carrying a component precisely planned for the installation sequence. Compressing a heavy, 2-lane steel motorway bridge into a reduced configuration required engineers to design multiple components that could be folded and rotated directly on site. Motorized components, such as the upper halves of the bridge ramps, could unload themselves using an integrated hydraulic system, while lighter, non-motorized elements were lifted into place by cranes. The installation sequence began with the lower ramp sections, followed by the curved transition modules that connect the road surface to the bridge deck. The upper ramp halves were then precisely driven into position, accurate to the millimeter, joined together, and secured with bolts to form a single unified structure. After each assembly step, the control systems of all modules were synchronized via software, ensuring the bridge operated as one integrated unit. The lower, non-motorized ramp sections were supplied with hydraulic oil from the upper ramps and, in theory, could also move on their own. During operation, the lower ramp sections and the curved transition modules rest directly on the asphalt surface, while the remaining components are stabilized by large steel base plates. The central part of the bridge consists of intermediate segments and motorized bridge portals, connected to each other by load-bearing pins. On the first night, the 2 bridge ramps were completed, allowing daytime traffic to continue flowing through the work zone in 2 lanes. On the second night, the bridge was fully completed using cranes that moved directly on the bridge deck itself. The maximum gradient reached 6.1%, and when the fourth bridge portal was installed, the deck reached a height of 3.6 meters. Each portal required about 30 minutes to unload and prepare. On paper, everything was carefully calculated. But only once real construction began did the engineers truly find out whether the plan would work as intended. In April 2022, the first deployment of the ASTRA Bridge on the A1 motorway officially began. More than 20 heavy-haul transport vehicles simultaneously left the staging area, each carrying a module of the bridge system. From that moment on, every minute mattered. A section of the motorway had to be completely closed for 2 consecutive nights. The challenge was clear. Within 14 hours before 10 a.m. on Sunday, a fully operational bridge capable of carrying traffic had to be completed and open to use. Within the first hours, the 2 ramp sections of the bridge were positioned and precisely connected. Cranes then began lifting and installing the intermediate modules under extremely tight site conditions. Every movement was planned in advance: vehicle placement, crane rotation angles, and the installation sequence. Each assembly, consisting of a bridge portal and an intermediate module, was allowed to remain on the construction schedule for no more than 30 minutes. To save time, the bridge was assembled simultaneously from both ends, after which the components were secured with high-strength bolts and electrical connections, forming a single integrated structure capable of carrying real traffic loads. Below, at that very moment, the construction crew began their road rehabilitation shift. A milling machine lowered its cutting drum into the old asphalt, removing the pavement to a precisely calculated depth. Meter by meter, the roadway was processed in a stable, controlled manner, with the milled material conveyed neatly behind the machine, exposing a fresh base for the next stages. Immediately afterward, an industrial sweeper moved into the newly worked area. Rotating brushes and a vacuum system collected all remaining fine dust and debris, thoroughly cleaning the surface and preparing it for asphalt resurfacing. This sequence was repeated in sync with each movement of the bridge system, within a confined space and under tightly controlled conditions. The construction crew continued by manually treating areas that machinery could not reach with sufficient precision. Workers used saws, jackhammers, and compacting tools to refine the milled edges and remove any remaining weak spots in the base layer. Dust and loose material were continuously collected, gradually revealing a uniformly roughened surface that met technical specifications. Following surface cleaning, the crew heated the joints and milled edges with gas torches to remove any remaining moisture and activate material adhesion. Immediately afterward, hot bitumen compound was injected directly into the joints, penetrating deep into even the smallest gaps to form a watertight, flexible bond. Next came the application of the tack coat and the placement of the new asphalt layer. Hot bitumen was fed directly from tanker trucks through flexible hose systems, supplying the paver continuously to maintain stable temperature and flow throughout the operation. The sprayer and asphalt paver moved slowly beneath the bridge, laying the new asphalt evenly over the prepared base. A dump truck slowly reversed beneath the bridge and raised its bed, releasing hot asphalt in a controlled flow onto the prepared surface. Workers guided the material by hand, spreading and leveling it evenly to ensure consistent thickness across the lane. As the asphalt settled, excess material was adjusted along the edges, keeping the layer uniform and well confined. Moments later, the fresh surface was ready for compaction, while traffic continued moving just meters above. Next, a finishing and cleaning unit moved over the freshly laid surface, using rotating brushes and suction to remove loose aggregate and excess material. At the same time, workers manually refined the edges with handheld air blowers, ensuring a clean, uniform texture before final compaction and curing. Next comes the placement of the final stone-mixed asphalt layer on the roadway. Paver ready in position. The asphalt paver is aligned to the correct elevation and center line, with its heating, drive, and grade control systems activated and ready for operation. Materials supplied from tanker trucks. Hot asphalt mix is continuously delivered from tanker trucks positioned outside the work zone, using smaller transfer vehicles. The supply process is carefully controlled to maintain consistent temperature and material uniformity. Loaded into the paver hopper, the asphalt is discharged directly into the paver's hopper, ready to be spread onto the road surface. Paver in operation. As the paver moves forward at a slow, steady pace, internal augers distribute the mix evenly across the full lane width. The screed at the rear levels the surface and sets the precise thickness and profile. Workers on both sides closely monitor edges and layer thickness throughout the process. Continuous paving process. The operation proceeds smoothly, meter by meter, within the confined space beneath the bridge. The final asphalt layer forms a uniform smooth surface, ready for compaction and reopening to traffic. Finally, the newly laid asphalt is compacted using vibratory road rollers to achieve the required density and structural strength. The rollers move slowly, making multiple passes in a pre-planned sequence to ensure a smooth, even surface without marks or deformation. Thanks to the bridge's stable structure, compaction proceeds normally while traffic continues to flow uninterrupted above. The ASTRA Bridge is an innovative solution for maintaining and repairing road infrastructure without interrupting traffic. It helps save time and money while creating a safer and more efficient working environment. However, the rental cost of the ASTRA Bridge is very high, ranging from $10,000 to $20,000 per day. Some people in China have commented that during the 14 hours required to install this bridge, they could have already finished repairing the road. What is your opinion on this? The use of non-stop mobile bridges for road maintenance is still a very new solution and has not yet been widely adopted in many countries. Meanwhile, traditional open-air repair methods, closing roads, diverting traffic, and carrying out construction directly, remain the most common approach due to their lower cost and familiar procedures. This contrast is exactly what makes non-stop bridge systems a topic of ongoing debate, balancing technological innovation against practical realities in infrastructure construction. The first step in this resurfacing process is milling off the old asphalt layer, usually between 2 and 10 centimeters deep depending on the level of damage. The machine grinds the old asphalt into small pieces, collects it onto a conveyor belt, and loads it directly into the truck behind. Milling removes only the worn-out top layer while keeping the underlying base and structure intact. This way, the road doesn't have to be rebuilt from scratch, which reduces cost and significantly shortens construction time. The milled asphalt, known as reclaimed asphalt pavement, is transported to a recycling plant. There, the material goes through a screening system to sort it by particle size and remove impurities such as soil, oversized stones, or metal pieces. The usable asphalt particles are then blended into uniform batches. This step is extremely important because RAP can have different levels of aging after years of service. Proper sorting and screening help control the quality and ensure that the recycled asphalt mix performs just as well as newly produced material. Once the RAP has been sorted, it's mixed together with new asphalt binder, fresh aggregates, and a rejuvenator. This additive helps restore the elasticity of the old binder that has oxidized over time. At the mixing plant, the RAP is gradually heated to avoid burning the aged asphalt, then combined with hot binder and aggregates according to a pre-calculated formula. Some modern asphalt plants can use 30-60% RAP, while still producing a mix that performs just as well as brand new asphalt. This step is crucial because it saves natural resources, reduces CO2 emissions, and lowers overall construction costs. Before the recycled asphalt layer is placed, the entire roadway surface must be thoroughly cleaned of dust, dirt, and debris to ensure maximum bonding. In this modern process, a single machine handles both tasks at once. As it moves forward, the front nozzles spray a thin layer of bonding material, the tack coat, directly onto the old pavement using asphalt emulsion or liquid asphalt. This layer acts like a glue that helps the recycled mix bond tightly to the existing surface and prevents any slipping or separation under heavy traffic. Right behind the spray bar, the same machine immediately places the recycled asphalt mix onto the tack-coated surface without any waiting time. The paver then spreads the hot mix to the design thickness, while the screed vibrates and compacts it continuously, forming a smooth and uniform layer with the proper initial density in a single pass. After the recycled asphalt is laid, both vibrating rollers and static rollers compact the mixture to ensure it reaches the required density, preventing future rutting or cracking. Once compaction is complete and the surface smoothness is checked, the roadway can be reopened, performing just like new. So that wraps up our look at the entire modern road repair process in Europe, where technology is used to solve traffic flow and safety challenges at the same time. From the mobile ASTRA Bridge to every construction step carried out underneath, each detail is carefully planned to minimize disruption and maximize operational efficiency. This is not just a story about road repairs, but a different way of thinking about smart infrastructure management in Europe. The information in this video was compiled from multiple sources, so if anything is inaccurate or needs clarification, please feel free to leave a comment so we can discuss and improve the content together. Thank you for watching, and we'll see you in the next video.